I got an email from the people that run the video system saying, "Are you happy to have your class on iTunes?" So, okay, so sent back. And then I got an email that said they'd put it up as new and notable, the first lecture. So it was sort of featured if you went to what's called iTunes U. And it still sort of shows up, not quite in the front page of iTunes U, but like if you go to the science page, it shows right up there.
Wait, is it for sale?
No. It's just, yeah.
Do you know if you can somehow like contact the person that told you and tell you to see if we can put up the video? Right now it's just audio, I saw that. Yeah. And this class can't be that useful with just audio.
Oh, no.
Is there something? Okay, because the last time I checked was a while back, but it was
You're talking about the university system?
no, on the iPhones.
No, iTunes are both there. You just click another tab. I tried to take a look, and when I clicked download, I got the audio, and then I realized I'd pushed the wrong button. Yeah. Of course, kind of weirded out looking at myself, so I didn't do that again. But okay. All right. I'm trying to remember where we stopped last time. I had, correct me if I'm wrong, because I forgot to note it. I had introduced the notion that if we have angular momentum and we have spin, that together they form J. Right? And then I argued that in quantum mechanics, let me repeat what I argued before, and let me try to put a little more into context. When we talked about the particle in a box the first time, and I said, gee, there's a lot of states. There's the n equals 1 state, there's the n equals 2 state, there's the n equals 3 state, and sometimes you don't know what state a particle is in. Well, in that system, actually, that was a little bit funny because the different states had different energies. And it's not usually the case you don't even know what energy the particle has. I mean, that can happen. But a more likely thing, but I think my statement about, well, you don't know what state it's in is, that's not the greatest example of it. These atomic systems now we're studying, an atom. There, it's a much more reasonable question to ask. If I tell you that the particle's in the n equals 2 state, all the different L states had the same energy. So what state is it in? It could have been in anything. Or even if I tell you it's in n equals 2, L equals 1, what's m sub L? So L equals 1, that meant, if L equals 1, that meant that the value of angular momentum was that, which in this case is root 2 times h bar. But what was the z component, right? That could have different values. It could have been 0, 1, or minus 1. So there's a similar thing here when I have these different, I have L and I have S. What's going to happen with them? And what I argued last time, and I'll argue again, is that typically to say that it is actually in some state, well, for these angular momenta, I said there's a z-axis. To say that there's now a z-axis which it will have some particular value relative to is to say that the particle interacts with something else. Or, in this particular case, as I argued, the orbit produces a magnetic field, the spin produces a magnetic field, so the two orient themselves relative to each other, at least if there's no strong external magnetic field. So what it boils down to is I can't just draw any arbitrary thing here. What I have to say is that, let me redraw it, and let's talk about just spin equals 1/2 for an electron. In principle, we could talk about 3/2 particles or spin 1 particles. Most particles you're going to deal with are spin 1/2, the electron, proton, the neutron. So let's talk about a spin 1/2, the electron in an atom. If here's L, and we'll even take, to be more concrete, we'll take L equals 1. The spin now will align itself its z-axis, if you will, is along the L-axis. And it can either align itself, well, let's go back to just all by itself. If I had a spin with this being z, it was either going to be in the ms equals plus 1/2 state or in the ms equals minus 1/2 state, right? And in fact, that was a 60-degree angle because the value of s itself is the square root of 1/2 times 1 plus 1/2 h bar equals root 3 over 2 h bar. And for something to have a length root 3 over 2 and then have a length 1/2, that's just a 30, 60, 90 triangle, okay? So that's what the spin could do, the S spin could do. Either have that component of z, an indeterminate amount of x and y, so you just don't know, or so it could be up or down. All right, and I think I mentioned that this state is often represented as simply down, and this state is often represented as simply up. Okay, if though, that's for an electron all by itself. That can happen. I can have an electron in a box. If the electron's not in a box, and it's in an atom, then it's also going to interact with the angular momentum, and the spin's going to decide to align itself either with or against L. In other words, that angle there, it happened to be 60 degrees, is the same 60 degrees here. So that, more to the point, the 1/2, m sub s equals 1/2 is the projection onto this axis. And so this is sort of, this is the L state when I align them. The J state, the J. And this would be J if they're anti-aligned. Okay? And so the way to think about it is that in fact, well, it shouldn't be surprising. So this is a J vector, that's a J vector. That associated with this J vector is a value J. It's completely analogous to the value little l or the value little s. And I've got to be careful with my notation here. This is capital S, the magnitude of the spin vector. Little s is this spin number, which is 1/2, which nicely describes the particle, although it's not exactly the value of the spin. Okay? Similarly, little l is this number here, like 0 or 1, but the value of the angular momentum is the more complicated square root of L times L plus 1 times h bar. So similarly, there's a J value, and the magnitude of the orbital of the overall angular momentum is J times J plus 1, square root of that times h bar. Okay? And here's the point I wanted to make. This notion that the spin is either going to line up with L or anti-line up with L turns into J is either L plus S or it can be L minus S. Okay? Or, in fact, that's for S equals 1/2. S equals 1/2. So as an example, for L equals 1 and S equals 1/2, J can equal 3/2 or J can equal 1/2. Okay? In general, little j goes from L minus S, I add 1 to it, dot, 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 up to L plus S. Okay? Why would this rise? Suppose L equals, okay, it gets more, there's just more to it than just add 1/2 or subtract 1/2 if S is 3/2. Or just a more common thing, suppose L equals 3. No, sorry. Confusing myself. this is needed if S is bigger than a half. So if L equals 5 and S equals 2, or L equals 5 and S equals 4, then you could run from 1 or 2 or 3 or 4 up to 9, okay? It's just, that's all. So it runs from L minus, the difference, add 1, all the way up to the sum. And that amounts to, and I'm being a little hand wavy here, but I don't want to spend a lot of time going into this. You can see, though, that's aligned with the idea that the S has to line up with, a long L or not a long L. But there's one kind of subtle concept I want to get across right here, which is actually, once it's done this, suppose it lines up. So here's my J, which came from an L in an S. It's in fact J. It's in fact J, which has a projection on the z-axis. And there would be multiple versions of it. You end up with a little letter j, and j sub z equals mj h bar, and m sub j, just like for spin, just like for L, mj runs 0, well, it runs from minus j plus 1, up to j. All right, it runs from minus j to j. The same rules as for spin, the same rules as for orbital angular momentum. And in this system, in fact, you don't know what L and S are anymore. You only find out what the overall angular momentum J is. Okay? Which is a slightly subtle concept, which will become important as you go on with your studies. I just wanted to mention it here. There's a notion of what are the good quantum numbers. Okay? If these are independent, then m sub L, m sub S would be good numbers. That is to say that if these guys were independent, the electron would be orbiting, and it would have a spin, and you could say that the z component of the spin was something, and the z component of the orbital angular momentum was something. That will happen if you have a large B field. You would define the B field as being in the z-axis, and these two will be independent. But if B is small, if there's no external field, then the argument I made is that the spin aligns itself along, the spin and L decide to both have a component along a mutual axis. They form a J, and only J and M sub J describe the system. These are good. Those are bad. Those don't exist. Yeah?
Would J and J also be good in the first case then?
No, they won't be. I know this is kind of subtle, and you're probably like, well, why am I telling you this? Well, it's a concept I'm telling you, and then we're kind of going to drop. Almost didn't want to tell you, but it's just sort of, I think it's an interesting way. It's an interesting thing that happens in quantum mechanics, is that Again, it's a form of the, it's somehow analogous to the uncertainty principle. When the spin and the orbital angular momentum interact, then they form the overall vector J. The overall vector J describes the electron, and the identity of the original orbital angular momentum and original spin are just simply lost. And in a sort of, kind of like a Heisenberg uncertainty principle-ish way, you can't ask about them. And by that I mean, like, if this thing is going to jump from one state to another, the state will simply be described by the J vector. You know, atoms do that. They have the various energy levels, okay? An atom left to itself without a strong magnetic field, you actually don't talk so much about L and M sub s and all that, and L and S anymore. You talk about the J value of the orbital, okay? And the book has sections. Now, we're in chapter 8, and there's the back of chapter 8 I've talked about a little. This business about adding L and S, I decided was interesting, and I talked about it. It's in the back of two sections. I believe they're 8.7 and 8.8, which we're, to a large extent, not going to cover. 8.8 and 8.9. I've covered a little bit. I just want to mention what's in those sections. This sort of distinction here, and also further discussions about what happens if you apply a magnetic field to the atom, and it changes the energy level subtly. It's a pretty detailed discussion in the book, and if you're really interested, I would invite you to read it. It's pretty tough going. It's an advanced topic. Why are they even in there? Well, the reason they're in there is that, I mean, it was a real triumph of quantum mechanics that you could get the energy levels of an atom. If you really want to describe what happens when you apply a strong magnetic field at the atom, turns out you've now got to start to count for something else. The electrons in an atom are moving at a pretty serious speed. They're getting a little bit relativistic, okay? And what we've done so far has not been relativistic equations. Why? Why? Because I simply wrote, in the Schrodinger's equation, here's my chalk. In the Schrodinger's equation, I wrote that energy was kinetic energy plus U, and I took this just to be p squared over 2m, and then the U is just U, right? If I want to include relativity, I've got to change this, and apart from the potential, I've got to say E squared equals p squared c squared plus m squared c fourth, okay? So now the p squared appears again, but I've got these other terms. And on the right side, I don't have energy, I'm going to have energy squared. And I am not going to talk about this at all anymore. I just wanted to point out that we were talking about a non-relativistic case, and there's a whole formulation of quantum mechanics with relativity, which is called QED, quantum electrodynamics, that was developed about 15 to 20 years after quantum mechanics. And it makes predictions for what happens when you put a strong magnetic field on an atom, and it also predicts small deviations from the simple Bohr atom energies and orbits that are predicted and that we calculated fully with non-relativistic quantum mechanics. And they're really exquisite predictions. There's these small deviations, they're called fine structure, and they're about a part in 10,000 of the basic energy levels. I think I mentioned this the last time, but I want to mention it again. And essentially, these simple atoms were like a playground for this developing field of the relativity combined with quantum mechanics. And the book does talk about this in a qualitative way and gives you some of the basic results. And it's spectacularly successful. Spectacularly successful. So the atom was a real playground. I mean, quantum mechanics came from the atom. Was, you know, the atom gave birth to quantum mechanics in some sense, right? It was, you know, describing atoms is why we invented quantum mechanics. And then not only that, but if you move from normal mechanics to relativity, combine that with quantum mechanics, you end up worrying a lot about this difference between a J and an L and an S and thinking about the magnetic fields. And there's this real triumph. And the author of our book, I think, felt like he just had to explain some of that. So you can look in the book if you want. It's a beautiful topic, but it's just It'll take a lot of time to go through it, so I'm not going to do it. But I just wanted sort of cultural awareness to realize that it's more than just the simple Bohr, call it simple. It's more than the treatment we've done so far. You can look at these fine details of the atom, which are due to next effects. The energy of interaction between L and S, which I haven't even mentioned, but it's there. I mean, I did mention it, but we didn't talk much about it. Okay, and so then so that's it. So that's as much as I want to talk about the the basic electrons in an atom in terms of this sort of thing. Okay, any questions? All right. Okay, so now I want to talk about something else that's in this chapter, which at first thought you would think is maybe completely unrelated to this spin and angular momentum. And that is, what happens if I have more than one particle? Your first thought might be, why in the world did we wait till now, or is it in the same chapter as the chapter all about spin and angular momentum that we talk about more than one particle? And, well, I will develop the answer to that question, okay? It turns out it's deeply related. And in fact, it's one of the most important concepts in all of quantum mechanics. But I have to work up to it. First off, so how am I going to describe more than one particle? Let me just state without fully justifying, but it makes a lot of sense, that what I should do is the Schrödinger equation should be modified. So let's think about two particles. 1 and 2. I'm going to work in one dimension for simplicity. The Schrödinger's equation becomes this. Well, let me write it down and then talk about it. Is that thunder? Yikes. All right. So I did a very simple thing. Although even though it's simple, I realized, there was some meat to it. I mean, I could have gone in a number of directions here, and I went in a particular direction. I essentially add the kinetic energies of the two particles, if you will. Minus h bar squared over 2m times this derivative squared is basically momentum of 1. I add the p squared over, that's kinetic energy of the first particle plus kinetic energy of the second particle. Makes total sense. Times a wave function which describes the both of them. This is the part that was maybe, I could have maybe had some choices. This is the right way to treat it in quantum mechanics. There's sort of one wave function which is going to describe both particles. Sometimes in the popular press you'll hear people will talk about the wave function for the universe, okay? All of real things include many, many particles, right? Very rare to get a particle all by itself. You can do it, but it's kind of hard. So most things are many particles interacting. The full treatment of any system like that, including everything in this room, is that there's a wave function that should describe all of it. It's one wave function, okay? And then this is just straightforward. If there's a potential energy that might depend on both particles, times the same wave function equals E times psi. Now, as usual, I don't know what to make of psi of two wave functions together. So what we try is psi of x1 times psi of x2. Okay? And so then my Schrödinger's equation becomes minus h bar squared over 2m. Let me just plug in. I'm going to go ahead and use the primes. And by this I mean d squared by dx1 squared. That's implied that I had x1 squared when I say I mean psi of x1 times psi 2 times psi of x2 plus psi of x1 psi prime prime of x2. Right, that's just straightforward. I'm just applying the derivatives, right? Equals, no, plus u psi of x1 psi of x2 equals e psi of x1 psi of x2. Just straightforward. I'll divide everything by the two psi's. Okay? I'll divide that everywhere by this. This will go away. This will go away. And that goes away. Oh, I erased the wrong thing. That goes away. Right, that's straightforward. It's the same separation of variables. But here the variables are not x and y. It's an x that describes particle 1 and an x that describes particle 2. Let me mention, just to be clear about this, I don't mean two different x-axes. I do mean, in this case, just a particle in one dimension. We're out of time, but I'll talk about a particle in a box. And I just mean simply, here's the box. It's from 0 to L in x. But I've put the label on the x just to look at the two different particles. And just to finish in a second here, if this is the case, well, I'll just finish here. We'll pick it up on Wednesday.